Objectives: to discuss the basic operation of a diode, discuss the basic structure of atoms, discuss properties of insulators, conductors, and semiconductors, discuss covalent bonding, describe the properties of both P and N-type materials, discuss both forward and reverse biasing of a p-n junction. The basic function of a diode is to restrict current flow to one direction. Forward bias, as in this direction, and reverse bias, as in this direction. This is a conventional or electron flow that they're showing here. The Bohr model of an atom, as seen in this model, electrons circle the nucleus. Atomic structure of a material determines the ability to conduct or insulate. Conductors, insulators, and semiconductors. The ability of a material to conduct current is based on its atomic structure. The orbit paths of the electrons surrounding the nucleus are called shells. Each shell has a defined number of electrons it will hold. This is a fact of nature and can be determined by the formula 2 times n squared. The outer shell is called the valence shell. The less complete a shell is filled to capacity, the more conductive the material is. The valence shell determines the ability of material to conduct current. A copper atom has only one electron in its valence ring. This makes it good as a conductor. It takes 2 times n squared electrons, or in this case 32 electrons, to fill the valence shell. A silicon atom has 4 electrons in its valence ring. This makes it a semiconductor. It takes 2 times n squared electrons, or in this case 18 electrons, to fill the valence shell. Covalent bonding is a bonding of 2 or more atoms by the interaction of their valence electrons. Certain atoms will combine in this way to form a crystal structure. Silicon and germanium atoms combine in this way in their intrinsic or pure state. Other atoms with 5 electrons, such as antimony, are added to silicon to increase the free electrons. This is an N-type material. Other atoms with 3 electrons, such as boron, are added to silicon to create a deficiency of electrons or holes, and this we call P-type material. With the formation of the P and N materials, combination of electrons and holes at the junction takes place. This creates the depletion region and has a barrier potential. This potential cannot be measured with a voltmeter, but it will cause a small voltage drop. Voltage source or bias connections are positive to the P material and negative to the N material. Bias must be greater than 0.3 volts for germanium or 0.7 volts for silicon diodes. The depletion region narrows. Voltage source or bias connections are negative to the P material and positive to the N material. Bias must be less than the breakdown voltage. Current flow is negligible in most cases. The depletion layer widens. In this case, with the voltage applied is less than the barrier potential, so the diode for all practical purposes is still in a non-conducting state. Current is very small. So here the forward voltage is less than 0.7, so we don't have current flow yet. With the applied voltage exceeding the barrier potential, the now fully forward biased diode conducts. Note that the only practical loss is the 0.7 volts drop across the diode. So all you're measuring is a 0.7 volts, even though the bias voltage is much greater than 0.7. An ideal diode characteristic curve is shown below. In this characteristic curve, we do not consider the voltage drop or the resistive properties. Current flow proportionally increases with voltage. In most cases, we consider only the forward bias voltage drop of a diode. Once this voltage is overcome, the current will increase proportionally with voltage. This drop is particularly important to consider in low voltage applications. The voltage drop is not the only loss of a diode. In some cases, we must take into account other factors such as the resistive effects as well as the reverse breakdown. Testing a diode is quite simple, particularly if the multimeter used has a diode check function. With the diode check function, a specific known voltage is applied from the meter across the diode. With the diode check function, a good diode will show approximately 0.7 volts or 0.3 volts when forward biased. When checking in reverse bias, the full applied testing voltage will be seen on the display. Note some meters show an infinite blinking display. So here, the diode check function is right there. On your meters in lab, there'll be a little picture of a diode. That's the button you would press. An ohm meter can be used to check the forward and reverse resistance of a diode if the ohm meter has enough voltage to force the diode into conduction. Of course, in forward bias connection, low resistance will be seen, and in reverse bias connection, high resistance will be seen. In the case of an open diode, no current flows in either direction, which is indicated by the full checking voltage with the diode check function or high resistance using an ohm meter in both forward and reverse directions. In the case of a shorted diode, maximum current flows indicated by a 0 volt with the diode check function or low resistance with an ohm meter in both forward and reverse connections. Diodes come in a variety of sizes and shapes. The design and structure is determined by what type of circuit they will be used in.